Here's a rolling problem that I want to set up using a problem you've probably seen before. Here's sort of a conservation of energy problem that might ask the following question here. Say you have a block here that's going to the right with a speed v. The question might ask, how high up does the block end up stopping? So as the block goes up the incline, it's going to stop right here, and we'd like to know how high up it goes. The way you do this with conservation of energy is you say something like, well, 1/2 mv squared is equal to something like mgh. You would just solve for h. So the kinetic energy that the block has down here on the flat surface all goes into the potential energy of the block at the top of the incline, and you can solve for h. And if you knew what this angle was in here, then you could potentially find the distance up the incline it goes, and so on, whatever the problem happens to be asking for. That's conservation of energy. So that's just sort of a setup for the actual problem I want to look at in this particular video here, is this one right here, where you have a ball that's rolling now. So it's definitely moving with a speed v, but it's also rotating this way with some angular velocity omega, something like that. That's not the way we draw the omega vector, because vectors aren't curved and so on and so forth. But in this case here, if we use the right-hand rule to put our fingertips in the direction of the rotation, they'd go around like that, and my thumb would go into the board. So if I wanted to draw that omega vector on there, it would be a vector which is sort of going like this. I see an omega vector sticking out of the wheel like that. But we'll draw the curved arrow on there just to denote rolling motion in my little picture here. Okay? So the question is the same then. We'd just like to know how high up the incline the wheel ends up going. And we'll use conservation of energy. So on the onset, though, it looks like a very similar problem. I could totally agree then that we say, well, the kinetic energy of the rolling wheel probably all goes into the potential energy that the wheel has when it rolls all the way up the hill and stops there at some point. And that would be a true statement, but it turns out that this isn't quite right for this here because there's another energy which we're not considering in here. So it turns out then that the way we know kinetic energy is 1/2 mv squared, and this holds for objects undergoing linear motion. There's the mass, there's the velocity. It turns out there's also something called a rotational kinetic energy. The 1/2 is still in there. Now instead of the m, we put an I. Instead of the v, we put an omega squared. Now, we're not going to go through any lengthy derivations about where this comes from, but when you think about where this might have come from, we have things like v is equal to v0 plus a times delta t, one of the simple kinematic equations. Well, we also have omega is omega 0 plus alpha delta t. And we have like F is equal to ma. Now we don't like the form of this, I'll just write it anyway, but we also have that torque is equal to I times alpha. So in this rotational stuff, we have a bunch of analogous equations that we sort of develop, and it's no different for kinetic energy. If linear kinetic energy is 1/2 mv squared, then rotational kinetic energy is 1/2 I omega squared, and we can just sort of use that to denote that there's some energy associated with the rolling motion, and indeed there is. So what you have to do in a case like this here is you can set up your energy once again. You can say there's 1/2 mv squared. Yes, there is some linear energy, or energy because of the linear motion, 1/2 mv squared. But there's also energy in the rolling motion. There's also kinetic energy in the rolling motion. Because it's rolling, rolling takes energy to happen. This is the moving energy, this is the rolling energy. They're both in there. All of that now is what gets transferred into the total height that the object has at the very top of the incline. Now, just a couple of things here. You have to look very carefully in the problem to see, well, exactly what type of object was rolling. Is it a cylinder, a solid cylinder, a hollow cylinder, or a sphere, what? Let's just say in the case like this, it's a hollow sphere. So you have to look on the chart here, and what we get from the chart, the moment of inertia chart, which is probably in your textbook, there's definitely one on Wikipedia you can find. The hollow sphere has a moment of inertia of 2/3 mr squared. And so you can fill some of this stuff in a little bit here. And what you'll get then is you have this kinetic energy term here, the 1/2 mv squared plus the 1/2. Now the I is 2/3 mr squared. Then you have the plus omega squared here times the omega squared is equal to mgh. Okay? So you're sort of moving along here. But now you have to be a little bit observant about the problem because you know that omega and v are related. In other words, the amount of the angular velocity this sphere has here is related to how quickly it's going this way because we want to roll without slipping. In fact, we know what that relationship is. We know that omega is v over r. This is the no-slip relationship right here. You can find that in your book, and it was probably covered in your class and stuff. So we can continue filling in some stuff in this equation here and get something like 1/2 mv squared plus 1/2 times 2/3. I guess I could simplify that into 1/3 there. I'll do that in the next step. Then we have the m right here, and there's definitely the r squared right here, but now you have this omega squared here, and for omega squared, we're filling in v squared over r squared. That's what omega squared is equal to, and all that's equal to mgh. Okay, so here will be the last step I'll do there. I'll let you finish up the problem here, but now what we have is we have this 1/2 mv squared term plus a 1/3. That's the 2/3, 1/2 times 2/3. Now look very carefully. This r squared is going to cancel that r squared, so you're just left with a 1/3 mv squared equals to mgh. So if you look really carefully, it's kind of bizarre though that you filled in the omega and you filled in the I, and now you have another term, which is sort of, you have another mv squared term. This is good old traditional kinetic energy for sure. And what this is here, this is kinetic energy also, but it comes from that rotation. So this is the linear kinetic energy that we're used to from linear motion. There's the rotational one, but we've just cast it into a form now, which you can combine to see what some total kinetic energy is. So in other words, I'm just saying that these two terms here, because all they involve is a different coefficient, can be added together. So 1/2 plus 1/3 mv squared is the total kinetic energy, and that all goes into the height of things. So I believe now with what you have here, you can solve this for the height, and you'll get some height that the object goes up the incline. And what I'll also point out is that the height between these two problems that I started in the analogous case here are going to be different. So if you have a block which is just going, sliding along the ground here, all of its kinetic energy goes into lifting above the ground, where in here, there's rotational energy and kinetic energy. Those combined sort of go into lifting the block above the hill. So the answers will be different. They won't achieve the same height. And so that height you can solve for here, but I hope you see how the kinetic energy terms were combined here. You can get sort of an equivalent not a half mv squared term, but an equivalent mv squared term there at the bottom.